Okay. So, let's see. First question up there, just as kind of a review, because we're going to see these things later on as we start talking about things called parametric equations. Just out of curiosity, anybody worked with parametric equations before? Equation for x, separate equation for y. Good. Everybody's going to learn something then. That's always nice. Okay, so I need point-slope form of a linear equation. Can somebody tell me what that is? Point-slope form of a linear equation. Y equals, even right there, that's wrong, okay? It's not y equals, it's y minus y1 equals, okay, it's m times x minus x1, okay? And m, of course, represents the slope, and x1 comma x2, or excuse me, y1, represents the point. That's why we call it point-slope form. And one of the nice things about point-slope form is all you need is a point and a slope, okay? And this form is just as good as slope-intercept form. In fact, in some ways, it's a little bit easier because point-slope form just requires the slope, which every line requires a slope. Every equation of a line requires a slope and a point. If you put it in slope-intercept form, you've got to have the slope still, but you've got to have a special point. You've got to know where it crosses the y-axis. Okay, so that makes it just slightly more difficult. A little bit better graph-friendly form, but this should work just as well. And if I were trying to find this right here, so stop and think about this. We did a couple chapters on trigonometry. Okay, this is a trig function, and this is an inverse trig function. And I had you memorize a couple of things about the relationship between those. So if I have a regular trig function, what do I put into a regular trig function? Okay, we memorized it like this. Regular trig functions take angles and give ratios. So if you've got a regular trig function, you put in an angle and it gives you a ratio, okay? Inverse trig functions do the exact opposite. We put in a ratio and it gives us an angle. So let's identify a couple of the parts right here. This right here is a ratio that we're going to plug into the inverse sine function. That means what comes out is going to be an angle. So that means if I'm taking the cosine of an angle, I should get, for the answer to this problem, I should get a ratio. Okay? Any questions about that? Okay, so now we just think about this. Let's focus on the inside of this. This says sine inverse of x over 7. Now, we're very familiar with the sine function. What two sides are related by the sine function? Opposite over hypotenuse. So this right here is the opposite side, and that right there is the hypotenuse. So that ratio that we've plugged into the sine inverse function is the opposite side over the hypotenuse. So I'm going to draw a picture of this. Okay. Now, because it doesn't say whether this is positive or negative, I'm going to put it over here. Okay, in the first quadrant. That just makes it easy. And it says the opposite side is x and the hypotenuse is 7. Now, could we come up with an expression that represents this side right here, especially given the fact that this is a right triangle? Yeah, we could use the Pythagorean theorem. We could say this is a, so that would mean that a squared plus x squared. Make sure you do the two legs squared together. Okay, so we're going to square the first leg, square the second leg, add it together, and I end up with 49. If I want to know what a is, I could move this to the other side, so I'm going to subtract an x squared. And then how do I figure out what a is? Just take the square root. Now, when we take the square root, I usually have to put a plus or minus on there. Do I need a plus or minus on this particular one? I see a bunch of shaking heads, no. Can somebody raise their hand and tell us why we don't need a plus or a minus? Huh? Okay, it's in quadrant 1, so it's got to be positive. And stop and think about this. I drew it in quadrant 1 just out of convenience. But if I were to take this and I drew it in quadrant 4, which is where the range for sine inverse is. Remember, the range for sine inverse is from negative 90 to 90, quadrant 4 and quadrant 1. Okay? In that case, this opposite side would have been negative. Would it have changed the sign of the adjacent side? Nope, not at all, okay? So this would still be right, okay? So this picture right here represents the situation on the inside of these square brackets. The sine inverse of x over 7 is represented by this triangle right here. And that right there would be our central angle, or our angle in standard position. And then what do I want from this? What do I want to know about that angle? I've taken care of the inside stuff. I want to know the cosine of that. I want to know what the cosine is of this angle. I want to, taking this picture, what is the cosine? And what is the cosine ratio? What two sides? The adjacent over the hypotenuse. So the adjacent is the square root of 49 minus x squared, and the hypotenuse is 7. And that right there is what we get when we simplify that ugly trigonometric expression. Okay? You stop and think about this. What we've done is we've changed a trig expression. So an expression that had an inverse trig function and a regular trig function into an expression that just has algebraic expressions in it. That's it. No more trig. Okay, and that can be a huge advantage sometimes. Okay, any questions? Okay, those are going to come back, and those are very useful ideas. You'll see those again. So let's talk about what a parameter is. Okay, a parameter is a controlling factor or a constraint of a problem. So if you've got to solve it within these parameters, okay, you got to solve it inside there. Okay, they like control what's going on. Okay, so when solving a problem, it's often useful to break a problem down into smaller parts. We've learned that a lot. Kind of compartmentalize. If I can find the answer to this piece and the answer to this piece, then I can maybe put those together and solve the entire problem. Okay, when we were dealing with vectors, that was a perfect example. Vectors can be really confusing, but if you break them into a horizontal component and a vertical component and just realize, oh, if I'm going to add these vectors together, I don't have to do anything complicated. I'm going to add the horizontal components and I'm going to add the vertical components. Okay, so separating them into simpler problems a lot of times makes it a lot easier. So again, we break those into horizontal components and we break them into vertical components. And to some extent, we treat those completely differently. Okay, a lot of the same rules apply, but we can kind of compartmentalize. Okay, so we're going to talk about something called parametric equations. And what parametric equations allow us to do is they allow us to use separate equations, completely separate equations, to figure out what the x and y coordinates are. Instead of saying y is a function of x, and you plug in an x and get out a y, we do it in terms of some other variable. We call that a parameter, okay? And it's an independent variable. And we usually use the variable t for the parameter. Now, if we're working with trig functions, a lot of times we'll use the variable theta for the parameter. And if you think about it, we've got an English t and then we've got a Greek t there, okay? So we've got a t here and a theta there, okay? And if we're going to parameterize a curve, so there's a vocabulary word for you. If we're going to parameterize a curve, and we usually say curve for anything, even a line, we'll call that a curve, okay? Then we've got to do three different things. We've got to have an equation that determines what x is. We've got to have an equation that determines what y is. And we've got to have an interval for the parameter. So usually we'll call this a t interval or a theta interval. But we've got to have an interval for the parameter. So I've got a little problem right here, an example that we're going to take a look at. And here's what it is. It shows all three things that we need to parameterize a curve. So the x equation says x of t, and notice x is a function of t. When I plug in a t, the first thing I do with it is I subtract 4. Okay, that will tell me what the x coordinate is. And that's all it tells me, is what the x coordinate is. Okay. Y is a function of t, so y equals 2t plus 1. So when I plug in a t, I double it and then I add 1. Okay? And then this right here is the t interval. So I've got those three key elements: an equation for x, an equation for y, and then an equation for, or an interval for the t, an interval for the parameter. So here's how it's going to work. Okay? Alexis, you're going to be the parameter t, okay? So Alexis has to work within these rules. She can say any number that she wants between -1 and 4, okay? Nathan's going to be the x, okay? So when Alexis says a number between -1 and 4, He's going to look at the equation for x, and he's going to figure out, based on what Alexis says, this is what the x coordinate is. Okay, and Logan's going to be the y. So when Alexis says what the number is for t, Logan's going to figure out what the y coordinate is. Okay, now if you would be really nice about this, pick nice numbers and kind of pick them in order. Okay, yeah. It'll just make it a little bit easier. So what number do you want to pick first? Say -1. Yeah, she's in charge here, other than me. Pick -1. Okay, so we're going to pick -1 to start. Okay, now once she picks -1, okay, Nathan's got a job to do and Logan's got a job to do. Now, we're actually going to graph this on an XY plane, so we're not going to graph what Alexis said. We're going to graph what Nathan and Logan say. So Nathan, what's x? -5. And Logan, what's y? -1. Okay, Alexis, keep being nice, please. 0. Oh, that's awesome. And Nathan?
-4.
Logan? Okay. Keep it up.
1. -2.
Got an easy job, don't you, Nathan?
3.
She's in charge. -1. 7. 7.
4.
Okay, 4.
0.
9. Okay. All right. So think of each one of these. Think of Alexis as kind of like a timer. They chose t for a reason. A lot of times it's useful to keep track of where something is with respect to time and just figure out what its x coordinate is, where it is horizontally and where it is vertically. So we're going to start off like this. Because -1 was the very first time, and I'm going to think of it that way, we're going to think of this as t equals -1, and this is t equals 4. Okay? So we're going to call this is called the, initial point. This is where it all starts. And this is called the terminal point. So if I chart these out, I've got -5, -1. So I've got that one right there. I've got -4, 1. So -4, 1. -3, 3. -2, 5. -1, 7. And then I've got 0, 9. So it looks like this. Now, we started right here when t is equal to -1, and I ended right here when t is equal to 4. So we actually, the way we've done this actually makes some sense, because I started with the smallest value for t and ended with the largest value for t. It actually goes from here to here in a straight line, okay? And I'll put endpoints on here. Again, that's the terminal point, and this is the initial point. And I'm going to put some little arrows in here, okay? This indicates the direction of travel. So you can imagine that these two equations would represent where some particle is in its motion. And we could kind of think of -1 as 1 second before we started the stopwatch, because right here was where it was at t equals 0. So a second before we started keeping track of this, it was right here. When we start the stopwatch at t equals 0, it's right here. Then t equals 1, t equals 2, t equals 3, and then t equals 4, and then we stop it. And this is the only portion of the path of this, this projectile that we're interested in, okay? So this particle's moving around. It happens to be moving on a line, happens to be moving kind of to the northeast, okay? And that's all we're going to keep track of. And the cool part about this is you've seen lines before. There's nothing fancy about this. But using parametrics, we're able to start and stop wherever we want. In fact, if we wanted to do some funky things with this, we could make exactly the same path, but we could make it go backwards. Okay? So the line would look the same. It would still go from here to here. Okay? It just might do it in the opposite direction. So there are a lot of interesting things that can happen with parametrics. Okay, now when I draw these little lines right here, what I'm drawing is what's called the orientation. Okay? The orientation is... it's like the direction of travel, okay? Whoops. Okay, orientation is the orientation. So I should read my own notes here. So orientation is the direction of travel, okay? All right? Okay, any questions? Okay, let's do one that's a little bit more interesting, okay? And I would make sure you pay attention to this because these are pretty typical and we could do some interesting things with this. Okay, so on this problem right here, you'll notice that the t interval is a little bit different. It just says t starts at -2 and can be anything you want as long as it's bigger than that. So unlike on this one right here where we had a starting point and a stopping point, we're going to have a starting point, we're going to have an initial point, but are we going to have a terminal point? No terminal point. Now let's go through this and do this in a nice organized fashion. Let's start with -2 and then let's just go by 1. So we're going to plug in a -1, a 0, a 1, a 2, a 3, and a 4. And let's see where that gets us. Now you can do the x, then the y, or you can go through and do all the x's and all the y's. What I like to do is I like to figure out what points I'm going to use. Okay, and a lot of times this would be enough, but I'll give you a case where it might not be. And I like to figure out what these are. So if I plug in a -2, I get -1, then I get 0, then I get 1, and 2, and 3, and 4, and 5. If I plug it into the y, I get, let's see, this is a 3. Correct me if I make any silly mistakes. That's a 0. That's a 3. Where'd I go? Oh, -1, yeah, okay. If I plug in a 1, we're back to 0, and then a 3, and then I get an 8, right? And then I get a 15. Okay, any questions? Okay, we don't graph the t's, but we do graph these pairs because we're graphing on the xy plane. So I'm going to graph -1, 3, 0, 0, 1, -1, 2, 0, 3, 3, 4, 8, about right there, and then 5, 15. So it'd probably be about right there. And since we plotted these in order, we can kind of go like this. Okay, now be careful right here. I've got an end point right there. What do I put on this end? I put an arrow, okay, because it doesn't have to stop, okay? And I'm going to indicate the orientation by drawing a couple little arrows there, okay? And this is the initial point, and it doesn't have any terminal points. And if I wanted to go just a little bit further, I could say it's right here at t equals -2, it's right here at t equals -1, it's right here at t equals 0. And then so forth. Probably wouldn't have to graph all of those, but it kind of gives some indication of where it was. So if we thought of the parameter t as time, we're timing something on a stopwatch. Right when we started our stopwatch, first of all, what shape is this? Looks a heck of a lot like a parabola. Right when we started our stopwatch at t equals 0, where was this little particle on this parabola? It's right here, right? Right at the bottom, right at the vertex, right? Okay. 2 seconds before, it was kind of coming down toward the vertex, and then all the time afterward, it's just kind of following that parabolic path there. Okay, any questions? Okay. All we're after in this section is just kind of getting a flavor for parametrics and how they work. Okay, so the next thing we want to do is we want to say, well, that's pretty cool that you can graph it that way, and that looks like a parabola, but it's not the whole parabola. So we want to think, well, why is that? And what could we do about this? So, let's see. I better hustle up or pause this for a second. We're going to eliminate the parameter. And if I eliminate the parameter, here's typically how we do this. We solve one of the parametric equations for t, and then we substitute for t in the other equation. So here's what I'd like you to do for just a second. Take that problem right there, take example number 3, solve one of the equations for t, and then substitute it into the other one. Now, if you take a look at this, which of these two equations is the easiest to solve for t? Probably the first one, okay? So go ahead and take that x equation, solve for t, and plug into the other one.
I'm not gonna answer. The second time that I left out for
Okay. Okay, listen up. So if you eliminate the parameter, we get t equals x minus 1, right? If I plug that in here, I get y equals x minus 1 quantity squared minus 1, right? So if I take a look at this right here, does that look like this graph? It does, doesn't it? Okay. This is a parabola. What does the minus 1 here with the x do to the graph? Moves it to the right, and the minus 1 here outside the squaring moves it down. So move over and down 1, and it still opens up, right? The other thing that we could do to just kind of finish this off is we could say this works as long as x is greater than or equal to -1. So what we've done here is we've kind of cut off this side over here. And we're just saying if you start at -1 on the x and go forward, that's the part of the parabola that we're after. Okay? Okay. Let's take a look at this right here. This one is a little bit more complicated, but let's take a look at it and see if we can figure this out. This one says x equals 7 sine t, and this is y equals 4 cosine t. Now, are either one of those very easy to solve for t? They're not, okay? But take a look at this one right here. If I take this one and solve it for t, because normally we write y as a function of x, I'm going to get sine of t equals x over 7, correct? And where am I going to take this and plug it in? I'm going to plug it in right there. So that means I've got y equals 4 times the cosine of, whoops, this is a sine inverse, right? Sine inverse of x over 7. Now, does any of that look familiar? It should. This stuff right here was in the starter question. And so we had drawn a picture of it and all that sort of stuff. And what did it turn into? Turned into ugliness. Turned into a ratio, right? It is, okay, it's sine inverse because what I did is I took the sine inverse, I divided by 7, and then I took the sine inverse of both sides to get the t by itself. Does that make sense? So if you want the t by itself, first of all, divide by 7. You'd have x over 7, and then take the sine inverse of both sides. That would leave a t over here, and then sine inverse of x over 7 over here, okay? And then just remember what that turned out to be. That's exactly the same expression right here, and it turned out to be the square root of 49 minus x squared all over 7. So we're going to replace this stuff right here with the square root of 49 minus x squared over 7. So I get 4 square root 49 minus x squared all over 7. Now that looks pretty awful. Luckily, we don't have to graph very many of those, and if we did, we'd probably end up doing it on our calculator. Okay. One thing I want you to keep in mind, though, just to spot right here, and when you study this a little bit more in depth, you'll do things like this. What type of answers do I get out of x? Like, when we're doing these up here, I can get almost any number I want out of x except for anything less than -1. I could get any positive number I want. Okay, but think about the numbers that come out of this. What's the range for the sine function? -1 to 1. Okay, remember, we get numbers out that are as big as 1, we get numbers out as small as -1. So that means the biggest this ever gets in the x direction is 7 to -7. What's the biggest this ever gets in the y direction? 4 to -4. So if we think about what this looks like, it's going to go from -7 to 7 in the x direction. The biggest it could get in the y direction would be 4, and the smallest it would get would be -4. Okay? This actually turns out to be an ellipse, okay? Kind of an oval type shape, which we'll study a little bit more in the next couple weeks, okay? Any questions? Okay, let's take a look at this one right here. This one looks absolutely awful, okay? Usually we end up solving for t, but that would be a little bit silly in this problem. Wherever there's a tangent of t, what can I put in its place? I can put an x. Isn't that right there a tangent of t? So I can put y equals 7 times what? X plus 4. So what shape is that? It's a line. Cross the y-axis at 4, slope is 7. Okay, it makes that pretty easy. Okay, any questions? Okay. So you've got a couple problems on your assignment that ask you to create parametric equations. This is called parameterizing. Oops. Parameterizing a curve. Parameterizing a curve. Okay? So in order to do that, you've got to have an equation for x, an equation for y, and again, what we call a t interval. Okay? Tell it what type of t's are okay to plug in. So if you have something that says parameterize a curve or come up with parametric equations that describe this curve or this line or something like that, okay? And they don't specify what the t interval has to be, okay? It can be very easy or very difficult. So you'll notice on this one right here, it says complete a set of parametric equations that will produce the indicated graph, this graph right here, okay? So that looks like a really ugly thing to graph. It's a parabola combined with a sine function, okay? If they don't give you any guidelines at all, here's the easiest thing to do. This is almost like cheating. You have to have an equation with x. So why not just say x is equal to t? If x is equal to t, I rewrite this as t squared plus the sine of t minus 4, and that's it. End of story. Now, if they say something like this for some reason, if they say x needs to be t plus 1, this is very easy because all you're doing is you're just replacing every x with a t. This is not quite what we're doing here, okay? Where every x is, what do we put in its place? Okay, so I need to put a t plus 1 quantity squared, sine of t plus 1 minus 4. And it's literally that easy, okay? Now, they didn't specify what the interval had to be, so we can use any interval we want. Okay, on this one, you just assume that this is all real numbers. You can plug in any x value you want, so therefore you can plug in any t value you want, okay? Any questions there? Okay, getting close to done, and then we'll do some fun stuff, okay? So this actually this is a little bit challenging, and I guarantee you'll see this in Math 1060. This says, write a pair of parametric equations that will produce the indicated graph. The line segment that goes from 1, negative 1, when t is equal to 0, to 7, 9, when t is equal to 2. Okay, now stop and follow this for just a second. First of all, it's a line segment. Okay, it goes directly from 1, negative 1 to 7, 9. So it starts at 1, negative 1, and it goes to 7, 9, right there. And how long does it take it to go from here to here? 2 seconds. So this is t equals 0 to t equals 2. Okay, now we could do this problem very easily, okay, on this particular one because it starts at 0 and then goes to 2. Okay, but we're going to do it in a way that will make this next one easier because this second one's actually a bit more difficult. Okay, so here's what we want to do. Remember that point-slope form equation of a line? Okay, I'm actually going to make some points. I'm going to make some tx pairs. So when t is equal to 0, what is x equal to? 1. And when t is equal to 2, what is x equal to? 7. Okay, now think about this. I'm going to slide this up just a little bit, and I'm going to write in a different color. Y minus y1 equals m x minus x1. And the slope would be y2 minus y1 over x2 minus x1. Okay, what's taking the place of the x and y on these two? What's acting like the x? The t is, and what's acting like the y? The x is, right? Okay, so here's what we're going to do first. We're going to find out what the slope is. I'm going to do x2 minus x1. So that's going to be 7 minus 1. And I'm going to do t2 minus t1. So that's going to be 2 minus 0. So I end up with, let's see, a 6 on the top and a 2 on the bottom. So I end up with a 3, right? Okay, now, remember, x is, the x is acting like a y, and this is like the t. Okay, so I'm going to write down x minus x1 equals m, and then this is going to be, let's see, t minus t1, right? So x minus, what's this? 1. What's the slope? 3. And this is going to be t minus t1, which is 0. Okay? Now, I'm going to move this around just a little bit, and I'm going to write x equals, if I distribute through, I get 3t, and if I move the 1 over, I get plus 1. Okay? This right here, if I can get it to stay around, that right there is the x equation. That'll tell me where it is, where x is with respect to t. So let's just double check and make sure this works. If I plug in a 0, do I get a 1? Yes, I do. The real test is going to be, if I plug in a 2, what should I get? If I plug in a 2, I get out a 7. So does this work? Okay, so we want to do the same thing with y. So let me show you this again. Okay, can I erase this? Okay, let me write this whole thing down. Here's what we just did. We did x minus x1, and then we did, we did x2 minus x1 over t2 minus t1, and then I did, t minus t1. Okay, if I do the same thing to figure out the y's, it's going to be y minus y1. Can somebody tell me what I'm going to write right here? Okay, in terms of these guys. X's, y's, t's, it's going to be y's. Y's go on the top. It's going to be y2 minus y1, t2 minus t1. And then I'm going to have t minus t1. Okay, now the reason I show this to you is there's a problem on your assignment that actually kind of runs through that idea, and it's a lot easier if I show you this here. Okay, so let's figure this one out and see if this actually works. Okay, this is going to be y minus, what is y1? Negative 1. Okay. Y2 is 9. Y1 is negative 1. And then T2 is 2. And T1 is 0. And then I write down T minus, what was T1? T1 was 0. Okay? Now take a look here. This is going to be a plus 1. This is going to be a 10 over 2, so this is going to be a 5. And that's just going to be a t. So this is going to be y equals 5t minus 1. Okay, now, if that works, I should be able to plug in a 0, and what should it tell me the y-coordinate is? It should tell me negative 1. If I plug in a 0, I get negative 1, and that works just fine. If I plug in a 2, this better tell me I get a 9. And if I plug in a 2, I do get a 9. So do they work? They do work. There are the 2, and then the t interval goes from 0 to 2, and there are the 3 parts that it takes to parameterize a curve. Okay, now let me erase this stuff right here. Okay, that is not the only way to do that, but that way works for every type of parametrizing a line that goes from one point to another point, regardless of whether we start with t equals 0 or t equals 5 or something like that. Okay, here's the hard part. Okay, this problem is much more difficult just because they don't start at t equals 0. That t equals 0 is a huge deal. Okay, so if you rely on the formulas, basically we're making a linear equation for x and a linear equation for y. It's just that they're based both on t rather than on x's or y's. Okay, so this, I expect that this would take some time to think about and figure out why it works the way it does. But if I were going to set up this one, again, I'm going to write this one down as x1, y1. This is t1. This is x2, y2, and t2. And then let's use these formulas right here. So this is going to be x minus, what's the first x coordinate? 2 equals, and then I do x2 minus x1. Well, x2 is right here. 7 minus x1 is 2. t2 minus t1. So that's going to be 6 minus 3. And then in parentheses, I do t2 minus t1, or t minus t1. So that's going to be t minus 3. And the one for y is going to look very similar. So it's going to be y minus y1, which is 1. Then it's going to be the difference between the two y's. So that's going to be y2 is 5 minus y1 is 1. 6 minus 3 is the same as it was over here. And t minus 3 is the same as it was over there. Okay, simplify that. Simplify the y. And then put the t interval on there and you're done. Now, what I want you to do between now and tomorrow at the beginning of class, you have some problems that use this. I want you to think about why this works the way it does. Okay, they actually, on the problem, they actually ask you to figure out how this works. Okay, so that's kind of part of your homework. Okay, are there any questions? Okay, does that seem too bad? Okay, take a look at this right here. I've got two more things that I want to take a quick look at. This is called a cycloid. And they're actually very interesting applications of parametric equations, and you can see why somebody might be interested in something like this. Okay, so here's what we've got here. If you've got a circle, a wheel or something like that, let's say we've got the valve stem. Everybody know what the valve stem is on a wheel, right? Okay, let's see we've got that, and we rolled it back here so the valve stem was sitting right at the bottom. And then we track that valve stem as it rolls around and around and around. So we're moving this forward. What's going to happen to the valve stem is it's going to go slowly upward, okay? Actually pretty quickly upward. Okay? Then it's going to get really fast in the horizontal direction. It's going to come down and it's going to touch for just an instant, and then it's going to get yanked back up. So this little black path right here represents the position of that valve stem. Okay? So these are cycloids, and they happen all the time, and they're very important in mechanics. Okay? There's an explanation of how you'd arrive at this stuff like this, but I want to take a look at this one thing right here. Let's look at the y coordinate right here. Okay, does everybody agree that the center line for where that valve stem is, it's below the center line, and then it goes up above the center line, and then below the center line, and then up above the center line. Everybody good with that? Okay. And when we start the stopwatch, it's right here. Okay. Partway through, it's going to hit the center. Okay. Then it's going to hit the very top right here, and then it's going to be back down at the bottom right here. Okay. Now, below the center line, then above the center line, and then below the center line. Is there a trig function that has a center line like this, where it would be below, then hit the center, then be above, then hit the center, and then be below? Is there? Okay. which one starts on the center line? Sine starts on the center line. Do we want it on the center line? We don't, so it's going to be a cosine. So let's say that this was 1 unit right here. How do I get the center to be 1 unit above the x-axis? And how do I get it to start below the x-axis, or below the center? If this was the center, couldn't I do a negative cosine curve and then move it up 1? Wouldn't that work? Okay, and take a look at this right here. See how that's, ignore the a right there. See that 1 minus cosine theta? That's what that represents, okay? So just want you to look at that, and then we're going to do a couple quick things. I'm going to keep you after for just a quick second. Grab your calculator. So we did some cool stuff with it last week. I'm going to clear this off. Okay, we need to do a couple things. First of all, put it in, hit the mode button. Okay, we want to be in radians. We do almost everything after basic trigonometry in radians. So hit radians. And then down on this one, we normally use function mode. You'll notice that we've got polar mode. We're going to learn about that. And we've also got something called PAR. That's parametric mode. Now, if I highlight that and I hit y equals, you'll notice that it looks quite a bit different. So I'm going to clear this off. Okay. If you were with me last week, you probably have a stat plot on. So highlight the stat plot and turn it off. That'll screw things up. Okay. And notice for each one of these curves, we've got an equation for x and an equation for y in terms of t. So I'm going to type in theta plus sine theta. So if I type this button right here, it knows it's in parametric mode. Whether it's t or theta doesn't really matter. Okay, plus sine of t. This isn't complete, and you'll notice the function doesn't turn on until I type the y equation. So that's going to be 1 minus cosine t. Close the parentheses. Now, this 1 right here, and the fact that there's nothing in front, means that we're dealing with a circle whose radius is 1 unit. So that means it's not going to go below the x-axis. Okay, and we're going to keep track of its motion going forward. So let's show mostly the first quadrant. So let's use 0 to 10 would be fine. 0.25 is okay. We're going to play with that in just a second. Okay, I'm going to go from negative 0.5 up to 2.5. Because remember, if the radius is 1, it's going to be a ball or a circle that's 2 units high. The scale is fine there, and then the y minimum, or sorry, let's do this. Negative 0.5. Let's go to 12. Okay, and the y minimum, let's go from negative 0.5 to 2.5. Everybody good? Okay, come back up here to the t step. Let's make that 0.1. We'll change it back to 0.25 in just a second. Everybody got it? Okay, hit graph. Does that look like it's supposed to? Somebody tell me why not? It's upside down. I've got a typo right here. It should be minus right here. I apologize for that. Let's go back here. Let's change that to a minus. There we go. Okay, can anybody tell me why it stops? Okay, we set the t interval. So if I go to window, and I go here, let's change this to like 20. That'll definitely get us off the screen. Let's change that back to 0.25. Anybody know what 0.25 is going to do to this? Watch and see if you can tell. Makes it go faster. Okay? And you'll notice it's still going there. Okay? All right. Let's see, tomorrow at the very beginning, I will show you how to do these last couple. They're pretty easy. Let me write down the homework so you can get started on it. So write this down. This is page 817. 1, 3 through 6, 9, 13, 16, 25, 29, 30, 37, 39, 40, 53, 54, 57, 59. Come tomorrow with about 7 problems done, and that's good. Do not do the whole thing. Don't do the whole thing.